All right, we're going to be YouTube famous today, so we'll all mind our language and stuff like that. All right, so we've learned some new tech about exponents. Exponents can be negative or fractions or zero. We've looked at graphs of exponential functions, talked about their domain and range, and then, as we usually do when we learn a new type of function, we start applying it to other situations. So today, we're going to focus in on just applications where we have exponential growth. So we have an increasing exponential function. You guys will note, I'm not sure why when I open up my notes in this program, it's dropping my f of x. That should say f of x. I'm going to blame the computer program. Totally not user error. It's totally, no, I would never make a mistake like that. For sure. All right. So we're going to take a real life scenario. We're going to create maybe a graph or two, but create an equation that models that scenario. And then I'm going to talk to you guys about the stuff we can do with the equation, at least at this grade level. So here's our first example. Population growth is a classic application of exponential growth. So we're going to focus on a brand new family of 10 rabbits. They settle down in a new briar patch, and the population doubles every year. Now, probably instead of family of rabbits, I should say like colony of rabbits. Because if they're a family, how's the population doubling every year? Seems a bit off. Let's change it to colony, in fact. Let's just change it to colony. Then there's no issues. Completely unrelated rabbits meet up, form a colony after the bunny apocalypse. They're repopulating the briar patch. All right. The population doubles every year. So let's just make a sketch. This is a simple enough scenario that we can all make a sketch of what's going on. The bunny population will start at 10. We don't have to think too hard about this. The bunny population starts at 10, and then every year it doubles. So from 10 to 20, and then from 20 to 40. I'm not trying to insult your intelligence. This is just how population growth works. I know it's a pretty simple scenario. 3 to 80. And then I think we cap out on our graph at 160. Look at that unchecked population growth. It just swoops up. Not a straight line. It's exponential growth. 160. All right. So I think my kids in grade school could have probably figured out how to make that graph. But what we want to do is we want to take that graph, this information, and make an equation, make a model out of it. But you guys just did this in the warm-up, so this should be no problem for you guys. But when we're modeling with an exponential function, often we'll use instead of y and x, we sometimes use variables that make sense for the situation. So for me, in this one, I'm going to model this one as p as a function of, I'm going to use t just for kicks, t for time. So p is for population, t is for time in years in this case. And then we just have a few blanks to fill in, just like our warm-up. Can you guys fill in those blanks to the power of t? This is a rule where things are changing every 1 year, so there's no funny business. It's not t over anything. Have we not just been doing this for like the last 2 days? Can one of you guys fill in the blanks for me? Fill in these. Maybe somebody hasn't helped out yet today. Emily E. 10 and 2. Fantastic. We start at 10, and the population doubles every year, and there we go. We now have an exponential function. So guys, any population growth scenario where we assume that the population can just grow forever and ever, you've got an initial value, and you have some information about how the population is changing. We can all do this. So I got to show you guys the two things that you guys in your grade levels have to be able to do with a function like this. The first is just plug and play. So we're going to find out what the population is after 5.5 years. After 5 years, it'd be 320. After 6, it'd be 640. But what is it at about 5.5 years? assuming our bunnies, I don't actually know the reproductive cycle of bunnies, how long that they're pregnant for, whatever. But we're going to assume that they can just multiply in between the years. We'll suspend belief here. We're not in ecology class. We're in grade 11 math. So you guys in this question are given a time, you plug it in, and you just do the calculator work. Okay, that's the first thing you guys have to do in your courses. Just be able to create a model, and then after you create the model, just do the calculator work. Now, your calculators, everybody should be able to do this just in one step. I'm not going to show any work here. My calculator can handle it just fine as I punch it in. 10 times 2 to the power of 5.5. Those of you guys who are doing this in multiple steps, it's very important. You have to do the power first. You have to go back to grade school and make sure you're obeying BEDMAS or PEMDAS. What do you guys call it nowadays? BEDMAS? BEDMAS for you? Yeah, PEMDAS is like parentheses instead of brackets. Fancy word, PEMDAS. All right, I'm going to round to the nearest whole bunny. 453 rabbits. Did you guys get that too? Nod and smile. It's calculator work, you guys. We should all be able to do it. Can you guys humor me? Can you guys pretend you have the misconception that you're going to multiply and then do the exponent? Can you just do 20 to the power of 5.5 and see what you get? 20 to the power of 5.5. It's a lot of rabbits. Clearly, us all being the intelligent people we are, if we did this by accident, we would think, oh, that seems really big. And then we would clue in, yes, I'm not supposed to do multiplication first. I do the power and then multiply. 453. Okay. The second thing you guys should be able to do is estimate when a population will reach a certain number. So please don't copy this down on your note. I'm going to erase it in a second because it's not part of your course. But what this question is really asking you guys to do is solve an equation like this, where you're given the y value, and you have to solve for the exponent. You guys currently don't have the skills to isolate for a variable in an exponent. So at the grade 11 level, the expectation is we use educated guess and check to do problems like this. So that's what we'll do. We'll try some numbers. So clearly, after 5.5 years, we're not even close to 10,000. So let's try some numbers that are higher than 5.5. No, I'm going to try, I don't know, I might try 10. I hope I'm not right on accurate with 10, but I'm going to try 10. I'm going to try p at 10. So that's 10 times 2 to the power of 10. We'll see how close we are. It's educated guess and check. Almost right on? Yeah. Of course. All right. Yeah, it's like just over 10,000, right? 10,240. Okay, so we got pretty good. Can we all just suspend what's currently going on? I got pretty lucky actually here. I guess 10 right away. But like, let's say you tried 15 and you got a number that was way bigger than 10,240. Well, then you would refine your guess and go a bit lower. So let's actually just kind of keep going. Let's see how close we can get to 10,000. So P at 10, a bit too high. Let's see if we can get closer to 10,000. Let's try P at 9.5. So we're a bit above, so we refine our guess. Let's try 9.5 and see what we get. Okay, so let me get my answer too. And I hear the exact process you should be going through. Just, if you're too low, oh yeah, this is really low. 7,241. So then we'll try a bit higher. Now I'm going to try 9.8 just to be different. $8,914. Still not close. I'm going to try 9.9. So I am using the method of educated guess and check, and I just adjust my guess till I get as close to my desired goal as possible. All right, I got 9,554. So unless we wanted to go to even higher accuracy, which one's closer to 10,000? Is it 9.9 years that we're closest, or is it 10 years we're closest? It's 10 years. 10 years, this number is closer to 10,000. So we're done. We can just say 10 years. I'm just going to tuck in a little about 10 years. People taking the grade 12 functions course, you will learn a method to solve equations like that. The 3M people, it's not required if you choose to just take data management. What is required is this idea of just being able to refine a guess until we get close to our answer. So if you guys, when you're doing an assignment for me tomorrow and you're asked to show this process, just show me you adjusting your guess until you get as close to the answer as you can. All right, those are the two things you guys have to do after creating a model. Now, this scenario was pretty easy to model, doubles every year. In real life, that doesn't always happen. So here, oh good, I'm glad I kept it PG here. This is a colony of 100 rabbits. So no issues. They settle down in Acton. Triples in size every 4 years. Our equation would change. Let's still use P for population, T for time. But this time we are going to need all of our 3 blanks. T divided by blank. Can you guys fill in the blanks for modeling a scenario like this? Maybe somebody that hasn't helped out yet today, can you help me populate our 3 blanks? No pun intended there. This is a little layup for participation. We'll take you from an N to an S or an S to a G. Sullivan, go ahead.
Oh, I was going to say, I got the exact number for 10,000.
Oh, okay. Did you? I'll come talk to you later.
Okay.
Yeah.
I did a lot of shit.
Sounds good. Can you somebody fill in the 3 blanks for me? Madeline's got them. It would be. 100 is the initial value. 3 for triples. And then, yeah, it's every 4 years. All right. You guys think you can model a scenario involving exponential growth? If you just had the info, you can pick off the initial value, the growth rate, how long it takes. Seems like we're doing okay. All right, let's continue then. All right. Another example of exponential growth, and this actually, our next unit to finish off the year, is all about this. It's all about finance and things appreciating in value. So we're going to dial in on next unit, mostly investments, but things like antiques, things like cards for those who collect them. I'm not sure what other things people collect, like watch Antique Roadshow. But things generally, like cards, appreciate in value over time. Some things appreciate in value over time. Things like cars and stuff like that depreciate. We'll talk about that tomorrow. Anyway, I digress. Bort bought a Jose Bautista rookie card for $20. Do you guys even know who that is anymore?
Yeah.
Okay, we still know who Jose Bautista is? Okay. It's like the last time we had something good to cheer for the Blue Jays. Anyway, he thinks that this rookie card will double in value every 5 years. So just based on the last example, you guys should be able to create a model for this scenario. Let's just choose some things that make sense. So I'm going to use V for value just for kicks. And then I'm just going to change things up. I'm going to use N for the number of years. I'm not your dad. You can use whatever variables you want, but they should usually make sense for the problem. So V for value, N for years. I'm going to let you guys create the model. And then part 2 is a plug and play. 48 years, I want to know what the card is going to be worth. I'm actually going to let you guys wrestle with 2 for a second. I'm going to do my attendance, and I'll come along for the ride. Very similar to the last question, except this time you're going to be doing an evaluation, 48 years, when there's something in the exponent, we'll be dividing by something. Anyway, yeah, you guys can struggle for a second. I'll pause the video, mute the screen, and just do attendance real quick. All right, we'll continue whenever I can get my tech to work again. We'll do the old unplug, wait for 10 seconds, plug back in. All right, guys, can we dial back in, please? My anticipation is that coming up with the equation here, not so bad for you guys. Its initial value is 20. Double means 2 every 5 years in the exponent. So your equation would look like this. So 20 times 2 to the power of n over 5. Now, actually, working with this equation, my anticipation is that not everybody was able to do it. So 48 years. We're plugging in 48. This one's a bit different. In this question, we have an extra additional divided by 5 in the exponent. Unless you're really good with brackets on your calculator, my suggestion for evaluating this is actually just going to do it in 2 steps. I do this in 2 steps. I do 48 divided by 5 first, which is 9.6 if I'm not mistaken. And then my calculator has no issue with me punching in that exactly as I see it, 20 times 2 to the power of 9.6. But when you do 2 to the power of 48 divided by 5, unless you're using brackets and putting things in properly, it's possible that you... So I got 15,520 and 94 cents about in 48 years. Of course, this is just a made-up fictional scenario. I'm pretty sure that he wasn't that good for his rookie card to be worth that much. Maybe it is. All right. Now, just maybe if you guys can humor me, I'm going to show what you get if on my calculator, if I do 20 times 2 to the power of 48 divided by 5, and I don't use brackets. I'm guessing some of you guys did this when you're trying to evaluate it. You get this. You get 20 times 2 to the power of 48 and then divided by 5. You get 1.13 times 10 to the power of 15, which is like 1 billion, trillion. It's like $1 quadrillion, which definitely seems off. So you guys should be using your just common sense. Ask yourself if your answer makes sense before you jot it down. All right. All fun and games so far. We do have to handle scenarios where we don't double or triple, but we increase by a percentage. This is what we'll be spending a lot of our time next unit doing. So in this question, Bort has borrowed $2,500 on a credit card, and Bort forgot to pay it off. Now, we're suspending belief in this question because a credit card company would not just let your balance grow for a year. You have to make a minimum payment. But we're just going to keep things simple for now. So let's just assume that Bort's $2,500 balance has just grown unchecked 4% every month. So let's create a model for his balance. I'm going to use B for balance, just for fun. And let's use M for month, just to mix things up. Just to emphasize, you can use whatever variables you want. They should just make sense. Balance, and squeeze this in here, month. Can you guys fill in the blanks? I'll have a couple sips of coffee while you guys do that. It's just every month, so we don't need M divided by anything in the exponent. what are you going to pop in for the initial value and the base if his debt is growing by 4% every month?
The question 2 says, how much will he have after 1 year? So how much will
Okay, so clearly I made a mistake. You know, every time you guys make a mistake, I don't laugh and giggle and point at you and say, "Jeez Louise, harsh critics." Jeez. Yes. Clearly it should say have. Okay. I'm gonna go home and cry myself to sleep tonight because you all made fun of me. All right, guys. So in all seriousness, my anticipation is that most of you probably didn't know what to do for the base. The initial value here, 2,500, is clear enough. But maybe you thought the base, if you thought the base was 4, well, the base is not 4. 4 means multiply by 4 or quadruple. And it wouldn't make sense for Bort's debt to go from $2,500 to $10,000 in a month. That'd be weird. It's not 4. Anyone have any ideas about what the base should be? Andrew?
1.04.
1.04, good. So the second thing students might try is using 4% as a decimal, which is wrong too, because that number is between 0 and 1, which would mean Bort's debt is actually decreasing, which would be great if you guys can find a credit card where your debt decreases over time if you just let it sit. Can you please let me know? Because I would want 100 of them. But Andrew is correct. We're going to use 1.04. Why 1.04? Because, and you guys can just add this to the side, every month, Bort owes basically what he owed before, plus an additional 4%. So he owes 104% of what he did the previous month. And then, as Andrew said, as a decimal, that is 1.04. And the hard part's done. And now we can find how much he has after 1 year is up. Note the change in units. This is something you guys have to be careful of too. This is just plug and play, but don't plug in 1. Our equation is set up for months. So you guys just have to make sure you're plugging in m equals 12 for 1 year, finding the balance after 12 years. And it's just plug and play. And then we'll wrap this up.
Yeah.
Did you guys get just over 4,000? The dangers of just putting money on credit cards and letting them grow. We'll explore that more next unit. All right. So let me end the video and then just have a little team talk.